All right, good morning. As I said, today the traffic condition might still be not very ideal for your classmates, some of them. So let's say we don't take attendance today. But I will still give you guys maybe 1 or 2 breaks in between, between the coverage of the subjects. And one thing very important to mention, okay, about the labs. Okay, for lab number 1, you know what you should do. The submission deadline will be next Monday. Just make sure you check the time very carefully. I want to mention this, which I did mention in the syllabus walkthrough session. So my regular office hour, you know when they are and where they are. I want to tell you about the TA. So I just updated the information on the E-class, just in case you haven't seen them. If you go to the E-class, 3342, and if you scroll down, you will see there's one TA's contact over here. So this is about the general policy. You can read it, very straightforward. But somehow it's not connecting. But if you click on that, you're going to see the email of one TA, Andy. Okay, let's not worry about it. But I already showed to you how you can find it. So Andy used to be an outstanding student taking the same course last winter, and he's now working for us as a TA. So I would say in addition to my regular office hour, if you want to speak to me outside, I'm happy to. But if you want to speak to Andy, he will usually be in the Thursday lab session in the Lassam building. And also, if you have any question, let's say outside of work hours, feel free to email him, and he will try to respond to you as soon as he can. If you guys feel that you cannot really solve the issue over email, he will be happy to Zoom with you. All right, so that's really some resources for you. You can ask him any questions related to course material, labs. The only thing you shouldn't really bother him will be the grading. Right? Any issues with grading, please speak to me in person. We don't really deal with grading issue over email. All right? Anyway, so you got the information. And for your lab number 1, just make sure you finish that in time and struggle through a bit, and then I'll try to see if I can go over with you very quickly about some highlights of the lab 1 solution. I'll make it available to you. And then you can expect your lab number 2 to be released by the end of the coming Monday. That one there is going to be also some interesting problem to solve. All right. And okay, if no question, why don't we do a very quick recap about what we said last time. Okay, over here. Okay, so what we said last time, let's go very quickly. Okay, starting from here. So we review all the basic operators for the set, intersection, union, set difference specifically, and also set equality, also subset relationship, proper subset relationship. You want to make sure you understand how to check the basic ones. And also how you can apply the bidirectional subset relations if you are having a return value being a set and input being a set. We also talk about it in detail, right? Especially if the specification only go one way but not the other. You should really know how to find some weakness to really show it is incomplete. We also discuss it, okay? And let's see what else. And we talk about 2 different formulas for power set. We'll still need this formula, interestingly, today, as I go over with you how to construct a relation. We'll get there. And we talk about cross products. It's really the basic units for relation. Okay, I'll review them once we get there. And we talk about some very basic distinction between relations and also non-relations. Minimum versus maximum as well. Make sure you get them, but we're going to review them today anyway. And this is where we ended with, about how you can calculate how to enumerate every member in a relation. Okay? Let's now take a look. Then we go through a little bit of slides, and then we'll do some exercise together. Okay? And then we'll go on to relational operations. Right? We'll talk about empty relation is a minimum, and cross product between the 2 sets will be the maximum relation from them. And we want to know this particular symbol over here about the relation. Okay? So now, whenever you want to declare a variable, let's say in Rodin, you want to say that variable there is a relation. How do you declare that? Okay? So there is a huge difference between this. I'll just clarify this right away. Okay? So there will be some notation you really have to get straight. When I say I have R, variable R, okay? If I say R is a member of, this is the notation you will have to know how to write. All right, so this one here is a relation. Okay. To be more precise, the set of possible relations on S and T. And this is the membership operator. And you're saying that S relates T is a set of possible relations on S and T. I'm saying that R is just a member of it. So R is a single relation. All right? So R over here is a single relation. On S and T. And this is what you will actually see on Rodin, how they visualize it. But how do you type it? The way to type it is something like this. You'll say R colon S less than dash less than T. That's how you type. You can think about this colon over here is really subset relationship. It's a very common symbol whenever you use a formal tool. Let's get that straight. On the other hand, we said before, let's say, let me just make it clear here. Let's say S will just be 1, 2, and 3. And also we got T, let's say just A and B. All right. Given this, okay, if I say R is a member of this, okay? So R could be, number one, empty relation, right? Just no pairs. Number two, another possibility, it could be the maximum, which would be just S cross product T. And how many pairs should be in that particular maximum relation? Should be 3 times 2, right? 6, okay? Just remember the formula. Good. And another one, let's say enumerated. It could be 1A and also 2B. Another possibility. We're going to enumerate them all. I'll give you the pattern in a moment. Okay. On the other hand, if I say another R2, okay? If I say R2 is a member of this 1A and also 2B, okay? This is where some confusion might come from. If you look at this thing alone, we know that this is a member of the set of relation between S and T, right? It's just a member. It's a member relation, first of all. And then I'm saying that R2 is a member of this member. Oh, sorry, said it again. This guy here is a member of the set of all possible relations between S and T. It's a valid relation. I'm saying that R2 is a member of this guy over here. What could R2 be? Would it be a set still? Not anymore, right? It would just be a pair. All right? Let's get it very straight. So R2 over here could be what? Could be 1A, or it could be 2B in this case. Nothing else. Right? It is so important whenever you see a membership over here, you want to draw a member from a certain set. However, that set over there may be a set of sets or set of relations, etc. So that's the main point I'm trying to make here. Okay, if you're okay with this, and let's now talk about how we can calculate relations. And I remember you guys made a very good observation at the end last time. When I was trying to show you guys how we can calculate all the possible relations over here, you guys told me that this process here is very similar to drawing the power set. Remember? Okay? That's why, not surprisingly, just for your information. Okay? Let's now do this exercise together. Okay? If I want to enumerate all the relations on A, B, and 2, 4, basically I want to get a set of relations. Each relation is itself a set of pairs. Right? To get that very clear. So there are two ways for you to formulate this. When you say all the relations on A, B, and 2, 4, right? There are two ways. You should know both, of course. Either you can say A, B, relates to 4. That's one way. All right. Another way is by using a power set. The power set of AB cross product to 4. This one here usually is more scary because you're using cross product and then take the power set. However, this one here really tells you how you're supposed to calculate the whole possible set of relations. So let's dive deeper into this. Okay? What this one is telling you is I'm going to calculate the cross product between these two sets, which is the maximum relation of that's on this particular two sets, right? Let's go step by step. If I just want to calculate this part over here, right? Just this part over here. I know that this part here is going to be the maximum relation on the two sets. And let's enumerate it precisely. Maximum relation, right? Is going to be a set of pairs, A2, A4, A2, A4, also B2, and B4. Right? I'm just trying to help you understand this part over here. Okay? It's a cross product, which will give you the maximum relation. Let's get that straight. And then, what does it really mean to take the power set of the maximum relation? That's the part that might be a little bit tricky. But since it's a power set, so we're actually going to follow the same step as we did for the power set before. It's just that now each member, rather than a single element, is going to be a relation. Right? That's something you got to be careful. Okay, so how do we calculate this? Now I'm going to add, let's say, we're going to do the power set of, I'm going to copy this down, okay, over here. It's going to be A2, and then A4, and then B2, B4. Okay. Now it's a power set, so I can ask you right away, what would be the cardinality of this power set by applying either of the two formulas that we talked about? 16. And that's your formula, right? Because we got 1, 2, 3, 4. Either to include it or not in the relation. In that case, 2 to the power 4. Right? That's one way to look at that. All right? Cardinality, by the way, the cardinality would just be 2 to the power of 4, which is 16. Right? That's something to note. But another way to look at that is by using the choosing operator to see what cardinality do you want for each relation. And then there might be different possibility. Let's take a look. All right, so let's try to do this. It's going to be a set over here. Each subset, each member, sorry, let me say it again. Each member in this particular set is going to be a subset from over here. A subset, for example, like this, let's say a subset that's going to include A2 and A4. It's a set of pairs, so it is a relation. Let me repeat, okay? Very important to see this. I want to calculate a power set of the cross product, which is over here, a set of pairs. If I calculate a power set, each member in the power set will be a subset of the set of pairs. And a subset of pairs itself is a set of pairs, which is a relation. So we are basically enumerating all the possible relations. That's what we are doing. All right? Let's try to do that. And the way we're going to do it is subset of size 0 or relation of size 0. What will be the relation of size 0? Empty. Very good. Thank you. So empty, this is relation of size or cardinality, doesn't matter, 0. And then we know that what will be the maximum subset, maximum relation itself, right? That would be just over here. I'm going to copy that again. A2, A4, B2, and also B4. So this one over here would be relation of size 4. All right, so let's make sure we understand these two. One here and one here. And we're going to go for another, what about other possibility? It should be all the relations of size 1, all the relation of size 2, all the relation of size 3. That's what's missing. All right? Why don't we do 1 or 2? I can leave another one to you for exercise. Okay? What about relation of size 1? How many do we have? There are 4. Did you guys figure? There are 4 pairs over here. Choose one. You can either choose this one here, this one here, this one here, or this one. Very good. Okay, let me write it down. It will be, for example, A2. Be careful over here, right? You can see I put the brackets over here around A2. It is necessary. I'm saying that it is a singleton set, which is a relation containing just one pair. It is still a relation. All right? And then another one, A4. And then B2. Sorry, I got to run out of space, but you see what I mean. B4. Okay? This will be the relation of size 1. Okay? And the formula we apply, 1, 2, 3, 4, is really about choosing out of the 4 pairs over here. I want to just choose one of them to make it a separate relation of size 1. It'll be just 4. And guys, very quickly, right? I promised that I got to give you some intuition. Okay? If you got n elements over here, you want to choose I. Okay? How do you interpret this? Basically, out of n given elements, no duplication. That's the assumption. How many ways to make a set of cardinality I, right? N here, N here, I here, and I here, right? How many? Okay. One way you can think about it is, oh, by the way, so when we talk about set, no order, right? So think about if this is the ultimate set you want to make. This is the ultimate set you want to make, right? Think about we got I different placeholder, right? A set of cardinality I. Just imagine that we got I placeholders over there inside the set. First of all, how many possibilities are there for me to really choose the first element? The first one. How many given elements? N. How many possible things I can choose for this first place? N. Agree? That's important. I put N here. What about the second slot? Would it be still N? Or n minus 1, why? Because it's a set. All right? The next one will be n minus 1. Next one, n minus 2, and etc. Basically, you want to do n times n minus 1 times n minus 2 all the way to some number over here. I'm going to work it out with you. But how many terms are we considering? I terms. But not done yet. Okay, this one over here should be about, let's say, n, I believe plus 1, something like that. Okay? Yeah. Anyway, I terms. That's the most important thing. But the problem is, if you only calculate this, it's going to include all the duplicates. For example, if you happen to choose a set, for example, if you happen to choose A, B, and C, Here, we happen to choose the first placeholder to be A. But the first placeholder can also be C. That can make you maybe CBA, right? So you're saying, so basically for A, B, C, and also B, C, A, and also A, C, B, something like that, right? So here you actually got duplicates that you want to eliminate. How many duplicates, basically? You want to divide it by I factorial, right? This one here. This part here might require a little bit more explanation. Try to work it out. If you cannot, come to me. I'll explain more. But I think that might just be enough just to understand this formula. To disregard duplicates. So the whole formula is going to be a division. This guy here for I terms divided by I factorial. So when you see the actual formula, it goes like this. N choose I, which would be n factorial divided by n minus I factorial and I factorial. That's what you will see normally. I factorial corresponds to this. N factorial divided by this is exactly this one because it's going to eliminate the final n minus I terms. So you got exactly I terms left over here. That's why. All right? Very quick recap about maybe something you already know, but just for your information, because you might need that to calculate the size. Any part you want me to explain a little bit more, feel free. Good? All right. Then assume you're okay. Think about it. All right, so we are not done yet. So for this relation here, we work out exactly 4 relations of size 1. So now I have some exercises for you, but before that, I can give you some hints. What's missing? Okay. A here, relations of size 2. Also missing relations of size 3. Now, let's work out. How many relations are there of size 2? Basically, how many sets out of 1, 2, 3, 4 elements can you make of cardinality 2? That should be 4 choose 2. Agree? 4 choose 2. According to the formula, you got 2 terms, 4 times 3, only the first 2 terms, divided by 2 factorial, which will be 6. Okay, one more, and then I'll leave you for this. 4 choose 3. Okay, 4 times 3 times 2, 3 terms. And 3 here, 3 factorial. 3 factorial is 6, and then you'll be 4. Right? By the way, 4 choose 3, just 4 choose 1. It's a property there, but you don't need to know. All right? And now that we know how many relations are really missing, I'm sure you guys can fill the blank, right? Try to work out exactly how many, find a good way to really enumerate. And you can go back to the power set and then to see some hints about how to, I actually gave you some tips about how you can enumerate all the possibility. All right? That's about how you can construct relations. It's really important to understand how to work it out. Okay? If we go back here, you will see that slide, right? That's exactly what we talk about. Yeah, you see exactly what I just worked out with you over here. Okay, all the way. And of course, you will really need to do a reasonably larger example to really get this completely right. How about this? I'll write it down for you. Let's make it more interesting. Let's say we have source. Let's say, sorry, let me say this. Departure. Let's say Toronto, Montreal, Vancouver. And let's say destination. And then let's say, maybe I'll just put some Asian city. Let's say Beijing. Let's say Seoul. I can put one more. Ping An. And that one's in Malaysia, just in case you don't know, but it's not important. All right? So we got 3 departure, we got 3 destination. And then we would say an airline is a member of all the possible relation between departure and destination. Because, for example, let's say Air Canada might support only from Toronto to Beijing and Montreal to Seoul, let's say, but not others, right? It's a subset, right? It's a set of pairs, right? And your job is to work out what's this. All right, task is to enumerate. I would suggest you do that, all right? If you want me to check your answer, bring it to me, all right? Okay, let's now move on. All right, so we are now done with the basics about relations. So from now on, we're going to talk about the various operations on the relation. So we can go a little bit faster, right? So we're just going to do definition quickly, and then we'll also talk about the different relation operators. Okay, I'll give you guys a little bit preview about what we're going to talk about. Okay, for today. And then, after the preview, we're going to take a short break, and then we'll start you fresh all the way to the end. Okay, we're going to talk about something called domain, range, and inverse. These are just warm-up. We'll do that first. All right, I just want to skim through what we're going to do today. Also, we're going to talk about image. That one's not too bad. That one is actually pretty straightforward, but you got to be careful. And then we talk about the so-called restrictions versus subtraction. So that one there, we got 4 possibilities. But I'll try to present them systematically. We got either domain restriction, range restriction, domain subtraction, range subtraction. And then we got something called overriding. All right? After that, we can do some exercises. But that's what we should do first. All right? Why don't you guys take a 2 minutes break, just get it refreshed, and then we'll get to the operation. Okay? Don't go too far, just 2 minutes. And as I said, we wouldn't take any attendance today.
Do you have an office hour today?
Yes, indeed. Yes, we do.
I mean, in person?
In person. In person, yeah. Yesterday was only yesterday was over Zoom. Yeah. Did you want to join yesterday? Oh yeah, I thought so. Yeah. I kind of sent an email to say, yeah, I won't be on campus. I was not on campus yesterday afternoon. So.
I saw it.
Yeah. That's okay. Okay. Yeah, I can come if you want to. The office hour. Yeah. Yes. Yes, in person. Yeah, I'll be on campus. Yeah, today's normal. Yeah. Mm-hmm. Luckily, snow stopped. Yes. For today, no, I'm not going to take attendance. Yeah, I just sent an announcement, but it'll be nice to see you. If no, then it's okay. All right, no problem. All right, guys, 1 minute, please, and then we'll have lots of fun stuff. All right, we'll start in just 1 moment. Alrighty, I hope everyone's fresh now. Let's talk about relational operations. Okay, you already had a preview before the break, but let's now go over each one of them. Okay, let's start with domain, range, and inverse. And then we can do a little bit of exercise just to emphasize, okay? Let's now have a running example over here. Let's say we have relation R. It's a set of pairs. That's what we assume. We're going to use all the operations on this particular relation, okay, just for illustration. And we got domain, range, and inverse. Domain and range are really, really easy. Basically, all the first elements are the domain. All the second elements of the pair are the range. That's intuitively. But I will encourage you guys to really convince you about the set comprehension again. I'll give you some pattern. Whenever you see some definition on the slides, there are several things I mentioned there. Let me talk about it, so I don't need to repeat for every one of them. Domain of R is how we say in English, natural language. And this will be just the intuitive definition, set of first elements from R. Typically, intuitive definition should be enough for you to do exercises. But I would say to be precise, you want to look at the definition here. And you can see for all the relational operation, because it's a set, so we can use set comprehension to define what's really corresponding resulting set for the operation. Okay? So for example, the domain of a relation will be all the D such that D and another second element will be in the relation, right? All the first elements, basically. So treat all the definitions over here being set comprehension as case studies for how you can write set comprehension. That's something I really encourage you to look at them. I may not be able to go over each one of them in detail, but you definitely want to look at them. All right, and then ASCII syntax is also something important. ASCII syntax is what you should type in Rodin. So here I'm trying to save you some time, so you don't really have to go to that cheat sheets, summary sheet I gave to you. So this one is accurate, but just in case you find any typo, please let me know, but I don't think so. I think all my students last year already checked for me, so it should be fine. Okay, let's go over one by one. I want to talk about domain and range. If you compare the set comprehension notation here, the range here is simply all the second elements where the second elements and some first element will be in the relation. Okay, like that. All right, let's now do exercise very quickly. Domain and range. All right, so if I want to calculate, let's say, the domain of R, very easy. I'm not even going to bother you. A, B, C, D, E, F. Make it a set, right? That one is going to be no duplicate, right? A, B, C, D, E, F, I believe. All the first. And what about the range? All the second. Range of R is going to be 1, 2, 3, 4, 5, 6. 1, 2, 3. Okay, so 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Very straightforward. Okay. Another thing, let's introduce it and we'll do the exercise. Okay. It's something called the inverse. Inverse means what used to be the first element now becomes the second element in the new relation. What used to be the second now becomes the first. You flip. That's why you call it the inverse. Okay? The way we define set comprehension make it very, very precise. You can think about what used to be like a D R prime in R. It's now R prime and D in the inverse. Okay? How do you write on the paper? You'll say R to the power of -1 on paper. And in ASCII, you will say R tilde. All right? That's how you do it. Okay, let's now do an example here. This one here, let's do it. It's very straightforward, but let's make sure you really, really get it 100%. The inverse, so I can say R inverse will be, used to be A1, now should be 1A. And 2B, 3C, 4A, 5B, 6C, 1D, 2E. Oh, you know what? Let me make a little bit more space for myself over here. 1D and then 2E and 3F. And it's a very simple property you can think about. The cardinality of R is simply the same as the cardinality of R inverse. That one's obvious. Of course, you can also argue about the contents, but we can do that later. All right, are we good? about all the three. They are very simple, straightforward. Okay? Now, exercise. How do you relate the domains and ranges of R and its inverse? How do you compare them? If I say the domain and range of R versus domain and range of R inverse, is the domain of R the same as the domain of R's inverse? What should it be equal to something else? The range, right? Okay, awesome. For example, you can see what used to be the domain over here now becomes the range, A, B, C, A, etc. What used to be the range has now become the domain. All right, let's write it down, all right? So the domain of R, the same as the range of the inverse of R. That's one thing. And also, the range of R is the same as the domain of R inverse. All right? And whenever you're defining this kind of property over here, it's called algebraic property. Algebraic properties. Okay. Okay, any questions so far? We all good? Okay. And next set of operations. Oh, sorry. Let's take a look. Image. All right. Whenever you're given a relation, and you can say, I want to get an image of some set. Okay, let's get the syntax right first. We'll say the relational image of R, the relation over some set S. Okay, that's the formal way, a little bit more formal way of saying it. Okay, we can just say relational image of S. Sometimes that's also fine, as long as the context is clear. I'll try to be as consistent as possible with the slide. The relational image of the relation over some set S. Notice that it's a set, not a single element. Okay. Simply it's a sub-range of R mapped by S. That one is not very clear. That's the limitation of a natural language. So what you really need is some formal language, like a math. The formal definition goes like this. Can you guys stare at this for just one moment here? On the left-hand side is the relation R and the square bracket like an array, right? Array indexing. And what's inside the little s is a set. On the left-hand side, we can read it as the relational image of R over set S. The right-hand side is what it should be. Okay? Guys, take a look at it for 30 seconds. Okay? It's not too bad, right? Okay? Basically, we are saying that for all the dr prime pair in R, we just want to make sure we get just the R prime. That's what we are saying. But of course, it is important the D here must be in the little s, which is the image over. All right? That's how you should read it. And how do you write it as ASCII key? Just array indexing, like this. Okay, let's do example. Okay, let's now try to do it. And really important to say, if you say R image over some S, right? Over here, this one over here is a set. Cannot be a single element. If you put a single element there, it's simply wrong syntax. Okay? What we can do is, let's try something here. Let's just try the first one by using a little bit more formal. Okay? The first one here, what's really the image of AB on the relation? Or image of the relation over AB. It's just a different way of saying it. Okay? Let's say we want to calculate this one. This one here, let me write it here. Right? It's basically R, which is over here. Image over AB. That's how you write it. Okay? By definition, it is simply all the second elements where dr prime is in R and the D is in this small set, AB. Okay? So now, visually, this is how I would calculate. It's AB here, right? So A, B, and that's it. So all the corresponding second element will be 1, 2, 4, 5. That's how I calculated the answer. Of course, you should know how to calculate. Also, you should understand the formal definition. That's both what you need. Are we okay with this? Sorry? Repeat what? Sorry. Sure. You mean the formal definition here? Yeah. Sure, no problem. When you say I want to calculate the relation of, the image of some relation over some little set, what we are saying is, think about all the pairs that's in the relation. We want to restrict only to the pairs where the first elements, the domain, matches any of the elements in this particular set. For example, for all these pairs, I only care all the domain value that's in either A or B. That's what I'm doing. Exactly. Yeah. Yeah, so guys, really try to get to like math. Maybe many of you don't, but in this course, it's really your friend. Right? That's the first one. Okay? What about this? What's the image of the relation over 1, 2? I heard empty set. Empty set. Anyone else? Empty set. Okay. Anyone else? The answer is undefined. Because when you want to calculate the image, this set over here is supposed to be some domain value you can do the image over. 1 and 2 is not even here. In some way, it's a category error. Okay? So let me put it this way. When you say S relation T, right? When you try to calculate R, an image over little s, the implicit assumption is that little s should be a subset of this. It should be of the right type. If you give the wrong type, then it's simply undefined. Not even like an empty set. I'll give you one example where it will be empty set. Okay, this is really important. Okay, undefined. What would be like empty? I'll give you. If I say R over here, let's say here, in this way, we are basically saying A, B, A, B. So these happen to be in the domain of the R. Okay? R could be, let's say we make the assumption. R over here could be a relation over all the alphabets. Relation, all the integer, right? But that's kind of implicit. But just the domain happen to be only the lowercase a, b, c, d. But there are other alphabet you can also do, like maybe x, y, and z. That's also fine in the alphabet. Right? So this alphabet over here is all lower and upper letters. So right now, if I say R over X and Y. So how do we tell this one here? You can see X, Y here are part of the alphabet. But X and Y do not happen to be the domain values over here in the relation. So that's why, what's its image? Empty. Okay? And I'll repeat the point once more. It's really important. The reason that this one is simply just undefined is because this one here is not even satisfying being a subset of the first set of the relation. This one here is empty because this one here is satisfied to be a subset of this, but it does not really appear as part of the domain in this particular relation. That's why it's empty. We can also use the empty set. Yes. Yes, also yes. It will work. By definition, yes. Not very useful, but we can do it, right? Okay? Now think about the definition. If this is simply just empty, that means there is no such D that will be in the empty set. In that case, there's no way to satisfy this constraint. So the resulting set for the image will just be empty. Okay? So guys, to really argue for this one being empty, you have to really go back to the definition. Because there's no such domain value that would be in this image set, which is empty set. So that means the resulting set, there's no way to construct any member in it. So that should be empty. Yes?
What if we want to find the image of 1 and 8? Will that be undefined or?
The image of?
1 and 8.
1 and A. What do you mean? You mean, okay, tell me what to write. I'm not exactly sure. Tell me what to write. You mean R of image?
Bracket.
Bracket, yeah.
1, 8.
This also is not good because 1 over here, this is not even, well, you can see 1 here is actually some second elements. You cannot use the second element for image. It has to be the first element only. Should be alphabet. And also A here, even though it's good, but you're putting two things of different kinds together in a set. That's not even right in the first place. Right? You see what I mean? Okay. But I'll just put over here, also undefined. All right. After discussing this, guys, how about this one here? Now, getting a little bit, you got to use some imagination. What about the image of 1, 2 on the inverse of R? Okay? So what you're doing is, you can definitely try to calculate the inverse of R. In that case, you will get this guy over here, right? And then from there, you want to get the image 1, 2. In which case, you're going to get 1, 2, and also 1. In which case, you're going to get A, B, and also D. Right? A, B, D, right? Let's write it down first. There's another way to look at it, A, B, D. So this one here will be A, B, and D. Another way to see, I can still use this relation here, but since you say the image of the inverse of R, so basically try to see everything that's 1, 2. 1 here, what's the corresponding first element? That'll be A, B, and D. That's another way to see. Am I missing something? Yes, exactly, E here. Sorry about that. E should be here too. Yes. Yeah, but you guys see my point. Thank you. Are we okay with this? Okay, calculate inverse and then the image. All right, so now, over here. How do you calculate R's range by an image? I'll write it down. It sounds a little bit weird, right? Okay, you can do that. I'm just manipulating the operations for you. So, the range, okay, I'll put it here. The range of some relation will just be equal to the image of R over what? The alpha? No, domain of R. Isn't that trivial? But it works, all right? You really need this kind of algebraic property to really help you think through how things work. Right? These are still the simple ones. We'll see the little more complicated one soon. And guys, how about this? How do we get a domain of R by image? Aha, I heard inverse. If you think about inverse, you're on the right track. Okay, I'll write it down and think about it. Okay. All right. For this one here, we're saying the domain of R will be the inverse of R. And then you can take the image of For example, let's think about it. The domain of R, you want to calculate basically just A, B, etc., right? And then what you want to do is you want to get an inverse, which will be 1A, 2B, 3C. And then you want to get basically this one here to really inquire, to be applied. Okay? That one will be the range. Okay, I'll write it down here. The range of R. This one here will take a little bit of thinking. Let me do it again, okay? If I do the R inverse, it's going to be something like this, okay? And I say I want to do the image over the range of the original R. The range of the original R will be A, B, C, and etc. So if I do the over the range of R, you'll be, oh, sorry, I'm confusing myself. The range of R here will be 1, 2, 3, 4, 5, and etc. I'm going to do exactly 1, 2, 3, 4, 5, and etc. to inquire. Okay? So what you can try is try to use this relation here, apply these two algebraic properties to see if that work. Okay? If you're not able to think abstractly that these two just work, you just need some example to help you. Okay? Try that. Okay? I'm sure these two are right, but you just gotta try that. All right, guys, okay? Well, you want me to do one example with you? Well, you're fine. You're fine? Sorry, which one?
Like under the highlighted one.
Yep.
Just like replace the R, range of R with the inverse of the domain R.
Yes, you can do that too. Yes, you can do the domain. Yep, absolutely. What your classmate was suggesting also something that's valid. You can also say the domain of the inverse of R. Absolutely. That's also fine. Yes, I agree. Yes, for sure. Yes. Domain to the this one here, no, because usually you don't really say the domain of this set over here, because this is not a relation. This is only a set. No. What you said was you want to replace this one by domain of alphabet. That's what you said, right? Just alphabet. That one there, you wouldn't really use this one directly. That's not the way to go. You really want to put a particular set. That's very concrete. No, you wouldn't put that. No. You simply wouldn't put that in the first place. Usually when you put the set over here, you need to be of certain known set. For example, a subset of a relation like this. Now you cannot just put alphabet. Let me look it up to see if that might be okay. But you wouldn't want to do that. Normally you want to be as precise as possible to restrict the range. Okay. All right, any question about image? All right, hopefully that's too bad, right? Okay, so now we're going to get on to 4 operations together. I'm going to present all of them together. Okay, so we're going to get, think about you got restrictions operator. Oh, sorry. There we go. There we go. You got restrictions operator. You also got subtraction operator. And think about each one of them. You also got, yeah, now I know how to present. There we go. Yeah, either it's a restriction or it's a subtraction. Okay? And then for each one of them, it could be you want to do over the domain or over the range. Either way. Okay? So these are the 4 operators we're going to see. But I'm going to write it down first, so it'll give you a preview, and we're going to see each one of them. Okay? Let's say we have a relation R, which would be, let's say, ST, right? Just in general. It's a relation. Okay? So the first one is called domain restriction. Domain is the first element, so it should appear on the left-hand side, right? So the input, little s, let's say little s, is a subset of the capital S. Okay? Little s, you will put like that. Okay? It appears on the domain side. It's a triangle over here. Okay? And what about range restriction? It should appear on the right-hand side. So little s should really appear on the range side. Like that. Okay? Subtraction is basically the same principle, except that you don't really have just a triangle. You should really put a minus inside for subtraction. Okay? So what about domain subtraction? Input here on the domain side, but it's going to be subtraction. Like that. And range subtraction. R. Like that. Okay? So you got to remember, understand the direction first. That's about the domain. And this part is about the range. Okay? And one is restriction, the other one is subtraction. If you understand this, then we can go on to define each one of them. All right, let's now move on. Let's talk about restriction first. Domain restriction and range restriction. Restriction means you're going to return another relation. Okay? In that new relation you return, its domain should be the same as the input set, little s. Well, here I put ds, like domain values. It should be the same. Well, let's take a look. And if you look at the formal definition here, let's try to read it. I'll read the first one together with you. Okay? I'll copy that, and then let's take a look for the first one. Give me a moment. I'll copy that down. Okay. It is a domain restriction. The result will still be a set of pairs. First value and also second value, R prime. Oh, by the way, the reason I'm using R prime rather than R, because we got R here already, right? Just you got to use a different name, okay? Such that, first of all, the D and R prime should be in the original relation. If you only leave things like this, it's going to give you the original relation. Agree? But restriction tells you got to give more constraint over there, so to restrict. Okay? And the constraint will be the D over here will only be included if it's actually in the input, ds. And the idea about range, restriction, and also all the subtraction operator follow the same pattern over here. So I only explain one to you. You can see others rather easily. Okay, that's restriction. And it's really important to note, what you get back is just another relation. So sometimes, don't be too surprised. Maybe you have to say, I want to get the inverse of the range restriction of this particular relation. And then maybe take another thing, right? You can build up the expression, okay? All right, that's good. Let's now talk about example. Domain restriction and also range restriction. And this will be what you have to write. You can see here, less than vertical bar is more or less, you know, the triangle I showed to you on the paper, right? And also here, vertical bar and then greater than. That's also to simulate that particular symbol. Let's take a look, okay? Okay, domain restriction. Let me see the example I want to show. A, B, and 1, 2. Okay, good. Let's do 2. Let's say I want to do domain restriction first. So triangle over here. Let's say I want to restrict to A and B. Okay, and then what about range restriction? So that would be restricted to this way, right? Let's say I want to restrict to 1 and 2. And that's the original relation. All right, how do we calculate these two? All right, of course, you really want to get used to the direction, right? Very easy to think about, right? I'm going to have another relation here, a set of pair. What pair should be restricted to? Only those where the domain value is either A or B. This one, this one, this one, this one, and that's it, right? That's domain restriction. Let's put it down. A1, B2, A4, B5. All right. What about range restriction? Similar idea, except that you're going to keep all the pairs. You're going to restrict only to the pairs where the second element will be either 1 or 2. 1, 2, and 1, 2. Right. So that'll be the result. That will be A1, B2, D1, E2. Okay, that's about restriction. Subtraction basically just go on to talk about what you don't want to keep, basically, right? Let me just do that directly on the example. I'll leave the definition, also syntax to you. All right, let's talk about subtraction. For subtraction, you can also do either on subtraction from the domain or subtraction from the range. Each one of them will still give you a brand new relation. Okay, let's take a look. So let's see. Domain subtraction. Put a minus here, and let's say we want to subtract AB. Range subtraction. Also, you're going to put range, let's say 1, 2. Right, you can see I deliberately chose the same input sets over here. But depending on we do this, or we do this or this, it will make a difference, right? You can contrast that. R here, R here. This one here, what does that mean? That means any pair whose first element is in A and B, A or B, you're going to get rid of it. Don't keep that in the resulting relation. Don't keep, don't keep, don't keep. And the rest will be there. Did I miss anything? Oh, you got a question, right? Yes. I missed one, I'm pretty sure. A, B, well, thank you. Yes. Maybe easier for you to see on the paper, I guess. Yeah. All right, good. Let me put it down. Right, it's going to be C3 and then C6 and D1, E2, F3. Okay. And just came to my mind. If you got a relation here, it could be just R domain restricted to some set, any set, union with domain subtracted by another set. Just another interesting algebraic property, right? Basically, it will be the original relation if you either you want the union, subtract, and also restrict. It will be the same. Give it a try, okay? I'll just give you that property, all right? Okay. Okay, finally, how about range subtraction? So here, I'm going to get rid of all the pairs where the second element is either 1 or 2. No, no, and no, no. Good. Which will be C3, A4, B5, C6, F3. All right. I hope everything is clear, but of course, you will definitely have to spend some time reading through, walking through this example again, and also look at the formal definition. That's really important, okay? Okay, let's move on. Okay, subtraction, we talk about. Overriding, okay? What about overriding? Overriding is a little bit tricky, but it's not too bad. You just have to know there are two cases for you to consider. Okay, let's say the same relation. we're going to say overriding of R with relation T. Here's the trouble. Remember about the image. Image is going to take some input set, just a set of single elements. Here, the overriding will take another input relation, which is a set, but it's a set of pairs. Right? That's something you want to contrast. Okay? So a relation which agrees with T within its domain and agrees with R outside the domain. It sounds very weird, right? That's natural description. Okay? But what about formal one? This is a formal definition over here. Okay? Let's try to read it maybe together. Okay? Take a look, and I'm going to copy that down. Okay? And then we'll take a look. Okay. Let's see. Okay. There we go. All right, there are two cases for you to consider. Case number one, oh, sorry, let me say it again. It will be all the pairs such that you got either case number one or case number two. Right, that's a general structure to think about overriding. Right, the DR pair will be included if either this is satisfied or this is satisfied. The first case, right? When we say it will agree with T, that one's easy. If DR prime is simply just a member of T, and don't forget T is an input in relation. Basically, T itself should be entirely in the result. Okay? This will be the first constraint. The second constraint is a bit indirect. Okay? The second one here is going to be something like this. I'll put a parenthesis so you wouldn't get confused about the operator. The DR prime is in the original relation. However, there is a however here. The D here cannot be in the domain of T, because if that's within the domain of T, it must agree with the T relation. Okay? D is not in the domain of T. Right? I'm just trying to help you understand the formal definition. Very precise, but it could be a little bit confusing. Recap, and then we'll do an example. When you consider overriding, it's going to be taking a relation, and the overall result will still be a relation, a set of pairs. Each pair either comes from the input relation T, or the pair comes from the input, the original relation R, given that the first domain value is not in the domain of T. Okay? You're gonna kind of disjoin, gonna decompose these two cases. Let's do example, and then you will see more clearly. Guys, any confusion about what I just said? If you maybe you want to take more time, right? But at least you're not confused. Hopefully not too much. You just need more time to think about it. Okay, talk about this one here. This one here, let's say we want to calculate the overriding. Let's say R overridden with, that's a symbol, and then a relation. A3 C4. Okay? By definition, it's going to be a relation, right? Which is going to be DR prime. Such that, okay, DR prime is a member of this input relation T. You can think about this guy over here is the T that we talk about, right? This will be A3 C4. And then, or the second case. Let me just put it here. I don't have space. Let's say or. Okay? And what about second case? D R prime is in the original relation R over here, right? That's the original relation. However, the D here should not be in the domain of T, which is A and C, right? Let me change the color of this constraint here. That's what you really want to pay attention to. Color? Over here. Are we okay? Great. Let's compute it. Right? Of course, if you can already do this one in the exam, you get some partial mark, but you got to calculate it, right? Let's calculate it. It's going to be union of all the pairs satisfying this and all the pairs satisfying this. This one here, just copy verbatim. A3 and C4. What about the second one? Anything? Isn't that something we already said before? What's this, really? I want to keep only the pairs from R whose first element is not A or C. Isn't that something we did before? Restriction or subtraction? Subtraction. Domain subtraction or range subtraction? Domain subtraction. Okay, I'm making a linkage over here, but there will be some exercise related to this. Okay, it's coming at some point. All right? And for your information, I can write it down since you guys are really following. Domain subtraction in a way. Meaning that I don't want anything to do with A and C. All right, so what I got left would be, okay, so I have B2, B5, D1, E2, okay, sorry, again, E2, and then F3. All right, that's how you calculate overriding. Are we okay with this? Good? All right. Overriding. And this, let me recap. Overriding, remember you got two cases over here. For the second case, it's as if we're doing some domain subtraction on the original relation R. All right? Okay, we got about 6 minutes-ish. Overriding done. This exercise over here, guys, I would suggest try not to peek the answer over here. Let me do the following. Okay, I want you to actually try to really rewrite these. Okay, give me a moment. Let me write the question here, and then I'll skip the slides. I really don't want you to peek. Think about it. Okay, there are two questions over here. Okay. Number one. So, problems. Don't look at the slides. Okay, number one. If you got a relational image, rewrite R image over little s over here in terms of domain, range, and or restriction subtraction. I'm not saying you got to use all of them. I'm just saying you might use some of them. All right, that's a hint for you. All right, think about how you can, given this particular expression over here, can you rewrite it to something that's equivalent using any one of any combination of domain, range, restriction, subtraction. Okay, that's some problem for you. I think that's reasonable. The second one. Okay, that will really help you review the operators we have seen. The next one will be overriding. Okay, rewrite the overriding. So when I say R, a relation overridden with some relation T, right? In terms of, okay, let's see. Similar. Domain, range, restriction, subtraction, and then one more. Some set operations. Union, intersection, set difference, that's what I meant. All right, so guys, these problems, yeah, to your greatest advantage, try to see if you can solve them. That will really push you to think. There might be more than one answer. If you somehow, once you're done, you can definitely take a look at the slide. I can go over with you guys very quickly next Tuesday. But I would say, before you take a look at the slides, really try to solve them. And if your solution is different, but you believe you're right, come to me. I can also help you. Okay, you're looking at this, right? Okay, can you promise not peek? Not peeking? Okay, go like this. Okay, there we go. Okay, functional property, right? We got 2 minutes only, right? What I want to do now is to talk about very briefly about function, and we can definitely finish the math review next time. We just need to talk about functional property. What's really a function? A function is a special case of a relation. That means a function is still a relation, but not necessarily a relation is always a function. That's the principle, okay? That a relation, when it's called function, that means it will satisfy the so-called functional property. That's the last thing I want to go over today, okay? Let's take a look, okay? That's the functional property. Let's take a look very quickly. I'm going to talk about this property here together with you, and then 1, 2, 3 question for you to think about, and then I'll go over answer with you. Okay, take a look. When we say a relation R is a functional, right? R here, yeah, just give me 2 minutes, and then I'll make sure I finish. It's a relation. A relation is also functional if you have ST1, T2. Think about R itself is assumed to be a member of S relation T. The little s is a member of capital S. T1 and T2 are of the second set T. All right, that's the context. Okay. If you can find ST1, T2 for all the combination, right? We say for all. Oh, that's exactly what I said actually in the antecedent. Right? So we're saying that if ST1 is in R and ST2 is also in R, that means T1 and T2 over here are the same. Okay? Can anybody try to explain to me what it is trying to say here? Nothing about duplicates. No, not duplicates. One or at most one. At most one. Very good. Okay? So here, let me write it down, and I'll give you one more, and then we can be done. Okay? Each domain value maps to at most one. Range value. A very quick example to show to you that's not a function. A1, B2, A3. This is definitely a relation. It's just a set of pairs. Is it a function? No. How does that violate the functional property? You can see ST1, ST2, right? You can think about here, this guy here is like a ST1. This one here is like a ST1. And this one here is like a ST2, right? We say that if you got such combination, then it must be that T1 is equal to T2. Is T1 equal to T2? No. That means the same domain value is mapped to multiple range values, right? So not a function. All right, good. Oh, we'll talk much more about function, injective function, surjective function, bijective function. We're going to talk about it. We'll finish that. Guys, thank you so much. Think about this problem here and this question. And then make sure you submit your lab in time.